Hello everyone, welcome to Brain Blitz Audios. Today, in this episode of NEET preparation, we'll be looking at previous year questions of physics in medical entrance examinations in India. Today we're dealing with alternating current. This is the 7th chapter in the grade 12 syllabus for physics in CBSE, and it is one of the most important chapters to be asked in previous year questions for physics. Let's begin with our very first important question, asked in AIMS 2015. A step-down transformer is connected to 2400 volts line and 80 amperes of current is found to flow in output load. The ratio of the turns in primary and secondary coil is 20:1. If transformer efficiency is 100%, then the current flowing in the primary coil will be. So, how do we solve this question? Here we'll be using the principles of a transformer. Now, if you don't know what they are, then you can always go back to our mind map on this chapter. Links down in the description. So, we have a step-down transformer, and it has 100% efficiency. We have the ratio of the turns in primary and secondary coil as 20:1. And what is also given is that 80 amperes of current are flowing in the output load. So basically, the current passing through the secondary coil is 80 amperes. We need to find the current flowing in the primary coil. Now, in order to start on this question, it is important to find out the relation between the number of turns and current in a step-down transformer. So I secondary divided by I primary is equal to N primary divided by N secondary. So this is the relation between the number of turns and the current in a step-down transformer. Secondary current is 80 amperes divided by primary current is unknown. NP divided by NS, the ratio of turns in primary and secondary coil, we can write that as 20 divided by 1. Now what we can do is we can write this as 20 IP is equal to 80. It's just cross multiplication. And you get IP as 80 divided by 20. Cut out the zeros, it's 8 by 2, that is 4 amperes. So the current that is flowing in the primary coil is just 4 amperes. And that is option C. So option C is the right option by using the relation between the current passing through the coils and the number of turns of the coils in a transformer. Let's look at our next question. The mutual inductance of a pair of coils, each of n turns, is M Henry. If a current of I amperes in one of the coils is brought to 0 in t seconds, the EMF induced per turn in the other coil will be, and we need to find this out in the standard unit, volts. So, how do we solve this question? Induced EMF can be written as M times di by dt, where M stands for mutual inductance. And in this question, we have number of turns as N and the mutual inductance as N Henry. So the current is brought from I to 0 in t seconds. So therefore, we can write this as M times N times I minus 0 divided by t minus 0. The reason why N, that number of turns, came here is for EMF induced in a coil of N turns. That will be equal to N times M times I minus 0 divided by t minus 0. I minus 0 is just I, and t minus 0 is just t. So this is the EMF induced in the whole coil. So our objective is to find out the EMF induced per turn. So basically, we can just divide the left hand side and the right hand side by n. So the left hand side becomes E induced divided by n, and the right hand side becomes NMI divided by NT. The n's get cancelled, so we have MI divided by T as the EMF induced per turn for the other coil. Now if we look at our options, we can find that option A is the right option, and all we had to do was to find out the EMF induced per turn using the formula for EMF induced in a coil, which is Nm di by dt. Next question. The tuning circuit of a radio receiver has a resistance of 50 ohms, an inductor of 10 millihenry, and a variable capacitor. A 1 megahertz radio wave produces a potential difference of 0.1 MV. The values of the capacitor to produce resonance is, and we're asked to take pi square as equal to 10. So we have the tuning circuit is basically an LCR series circuit. In this LCR series circuit, the resistance is 50 ohms. And since the L is 10 millihenries, it becomes 10 raised to minus 2 Henry, converting it to the SI unit. We also know that the frequency is equal to 1 megahertz. That is equal to 10 raised to 6 hertz. We need to find the value of C. How do we find the value? Now here, the value for resistance and the potential difference is not required because the formula that we'll be using does not require these calculations. What we're going to be using is the formula for angular frequency. The angular frequency, omega, has two formulae. One is 2 pi times the linear frequency, and the other is 1 divided by root of LC. So on comparing both of these equations, we will get 2 pi times the frequency as 1 by root of LC. The frequency is now equal to 1 by 2 pi times root of LC. So what we're going to do now is we're going to square both sides. So the left hand side is frequency squared, and the right hand side is 1 by 4 pi square times L times C, because these are out of their roots. Now what we do is we swap the position for C and the frequency, so the capacitance will be equal to 1 by 4 pi square times L times the frequency squared. So how are we going to solve this now? Well, all you have to do is just put in the values, because we have a formula to find the value of C. So C is equal to 1 divided by 4 times pi square, we take it as 10. And the inductance is given as 10 raised to minus 2. And the frequency is 10 raised to 6, which is under a square. So therefore, we have 4 into 10 raised to minus 1 into 10 raised to 12. Now all of that was the denominator. So now what we're going to do is we're taking this 10 raised to minus 1 to the numerator. So it becomes 10 divided by 4. And when we take 10 raised to 12 to the numerator, it becomes 10 raised to minus 12. And the unit for capacitance is farad. So 10 by 4 into 10 raised to minus 12 farad. So 10 by 4 is 2.5, and 10 raised to minus 12 farad is the same as a picofarad. So 2.5 picofarads is the right answer. And that is the right option, which is option A. So option A, 2.5 picofarads, is the right answer. And remember, we didn't use all of the values given here. We just used the values that were relevant to us, the inductance and the frequency. And we used the formula omega is equal to 2 pi nu, and omega is equal to 1 by root of LC. This is a very important question asked in AIMS 2016. A coil has a resistance of 30 ohms and inductive reactance of 20 ohms at 50 Hz frequency. If an AC source of 200 volts potential difference and 100 Hz frequency is connected across the coil, the current in the coil will be. So, for the coil, we have R is equal to 30 ohms, and it's going to stay that way. XL is equal to 20 ohms. And the frequency is equal to 50 Hertz. Let's apply omega is equal to 2 pi times F. So we can find out the angular frequency. So it'll be 2 pi times 50, which is equal to 100 pi. For the coil, if omega is equal to 100 pi, then the value of XL is equal to 20 ohms. So this is the situation when we're not connecting the potential difference. So once we connect the AC source, things change drastically. And let's find out how. So when you have the AC source, V is now 200 volts, but more importantly, the frequency is now 100 Hertz. So if we find out the angular frequency, omega is equal to 2 pi F, which is 2 pi times 100. So we would write it usually as 200 pi, but I like to keep it as 2 times 100 pi. And 100 pi is the same value as that of omega 1. So 2 omega 1. So as you can see, the value of angular frequency is twice that of the angular frequency of the coil. Now, using this relation, we can write that the inductive reactance of the source, that is due to the source, is equal to 2 times of the inductive reactance, which is standard of the coil. So that means 2 times 20, or 40 ohms. So the inductive reactance is 40 ohms, and our resistance is 30 ohms. We need to find out the current passing through the coil. And for that, we use Ohm's law. I is equal to V by Z, where Z stands for impedance. We'll use the formula for Z. Since this is an LR circuit, it'll be R square plus XL square, all of that under a root. So the value for V is 200 divided by R is 30 square plus XL is 40 squared, all of that under a root. It becomes 200 divided by 30 square is 900 plus 40 square is 1600, all of that under a root. Inside the root, 1600 plus 900 now becomes 2500, and the square root of 2500 is 50. So I is now equal to 200 divided by 50. That is equal to 4 amperes. So the current passing through the coil is 4 amperes if we have an AC source of 200 volts and 100 hertz. So therefore option A, 4.0 amperes is the right option. And for that, all we had to do was to use the formula for angular frequency, which is equal to 2 pi f for the two different conditions, and then use Ohm's law in order to find the current. Let's look at this question, asked in AIMS 2016. An ideal coil of 10 Henry is connected in series with a resistance of 5 ohms and a battery of 5 volts. After 2 seconds, the connection is made. The current flowing in ampere in the circuit is. So, in this question, we have the value of R as 5 ohms, the value of L as 10 Henry, the value of E naught as 5 volts, and the value of time as 2 seconds. What equation of current must we use? So we will use the equation of current, which is I is equal to I naught times, inside the square bracket, 1 minus e raised to minus RT by L. Now I naught can be written down as E naught divided by R using the Ohm's law. And inside the bracket, it's still the same, 1 minus RT by L. In this format, we can put in our values given. So the formula for I is equal to 5 volts divided by 5 ohms, inside the bracket, 1 minus e raised to minus 5 times 2 seconds divided by 10 Henry. So 5 and 5 gives you 1, and inside the bracket it's 1 minus e raised to, minus 5 into 2 is minus 10, minus 10 divided by 10 is minus 1. So the value of I is now reduced to the equation 1 minus e raised to minus 1. And if we look at our options, you can find that option A is the right option. For that, all we had to do was use the equation of the current. I is equal to I naught into 1 minus e raised to minus RT by L. And in this equation, we just replaced I naught as E naught by R using the Ohm's law. And then what we had to do now was basically put in the values, and after putting in the values, you can find that I is now equal to 1 minus e raised to minus 1. This is our final question of this episode, and it's a tricky one. Stay tuned. This is found in AIMS 2017. An inductor, a resistor, and a capacitor are joined in series with an AC source. Basically, what that says is we have an LCR series circuit. The question: as the frequency of the source is slightly increased from a very low value, the reactance of which of these increases? So option A, inductor increases. Option B, resistor increases. Option C, capacitor increases. Option D, circuit increases. So, how do we look at this question? Now, in this question, we have L, C, and R, the three components. R is constant with respect to omega, so R is not dependent on omega. When we look at Xc, or capacitive reactance, it is 1 by C omega. That means 1 by C times 2 pi nu, and where nu is the frequency of the source. So you can see that Xc is inversely proportional to the frequency. So as the frequency increases, Xc decreases in whatever value it is. If we look at XL, the formula for that is L omega. So therefore, it'll be L times 2 pi nu. So, which means that XL is directly proportional to the frequency. As the frequency increases, XL also increases. The right answer is option A, inductor increases. Option B is incorrect because R is constant. Option C is incorrect because in the case of a capacitor, the reactance increases. And option D, circuit increases. This is not possible because as we increase the frequency, XL might increase, but XC also decreases at the same time. So therefore, there is no net change due to the small value of the increase or increment or the decrement. So option D is incorrect. The right answer is option A. Inductor increases. The reactance of the inductor increases because XL is equal to L omega, which is equal to L into 2 pi nu. So XL is directly proportional to the frequency of the source. And that concludes this webisode of NEET preparation. For getting more of our useful and interesting content, don't forget to subscribe to our channel, Brain Blitz Audios. For getting more of NEET preparation, you can always click the link in the description down below. And also for viewing the chapter Alternating Currents mind map, you can also click the link in the description down below. So until the next webisode, take care, stay safe, bye-bye for now.